Here's a short, sweet video on half-life. Half-life is a first-order reaction. The graph here is a graph of concentration versus time. If we were to graph natural log of concentration versus time, we would get a straight line. Now, you often hear about half-life in terms of like nuclear reactions and decay. It's the time it takes for half of your original sample to decay, or half your original reactant to react. The concentration of your original reactant goes down by half. Now, again, off this graph, you can kind of estimate it. If my original concentration is 0.1, it's the time it takes for that concentration to go down by half to 0.05. My half-life then is about 100 seconds. Every 100 seconds, the concentration continues to go down by half. I go from 0.05 moles per liter down to 0.025, and so on. Now, again, it is a first-order reaction, so if we graphed natural log of concentration versus time, we would get a straight line. Now, here's what we used to have to do. Often you'll use this first-order equation, kind of like this. Here's how it's listed in the AP packet. Natural log of A, or whatever your reactant is, at time t, minus natural log of A initial times 0 equals opposite KT. And from K we can get the slope of the line, all that good stuff. Now, often we solve this for the concentration of A at time t, kind of like what we did in the last video, where they might say, after a certain amount of time, what is the new concentration of reactant A? Another option is to solve it for time. They might say, how much time does it take for the initial concentration of A to decrease by blah, to decrease to whatever? And that would become my concentration at time t. And we'd solve for time. So we used to have to solve half-life this way, actually, where they might give you the initial concentration, like they do here. And they say, initially this is like 0.1 molar. And then, even if we didn't have a graph, they could say, what's the half-life? And if we knew that half-life is a first-order reaction, we could kind of plug into this equation. We want to solve for the amount of time it takes for that initial concentration to go down by half. So at the half-life, this would be 0.05 molar. And then we might have like the value of K, and maybe we'd find the slope of the line, and the constant should just be the opposite of the slope. We'd plug it all in, solve for T. Which still works. It totally still works. However, I don't know why, but somebody must have been feeling really generous, and they gave you this cute little equation now on the AP packet. This is new. It says time 1/2, which means the half-life, the time it takes for the initial concentration to go down by half, equals 0.693 over K. It's kind of a plug and chug kind of deal. You just need to know your constant. Well, that's not so bad. You can plug that in and solve for the half-life. But conceptually, I think it's still important to understand that bottom equation. Half-life is a first-order reaction, and if I understand the definition of half-life, it's the time it takes for the initial concentration to go down by half. And so again, we could solve this equation for time t. And it might not even be half-life. They might just say, like, how much time will it take for the initial concentration to go down to whatever. And that would be another application of this first-order equation.